Okay, so we're going to take a look at page 390. All of the questions here are going to be using not just this, but definitely the equation 331 meters per second plus 0.59 meters per second degrees Celsius times t. Okay, so we're going to be using this guy. So number one says, what is the speed of sound in air at each of the following temperatures? So it's giving us the temperatures and it just wants us to fill them in here. So the first one, so 331 meters per second plus 0.59 meters per second degrees Celsius, and the first temperature is negative 15 degrees Celsius. Okay, and so when you do this, you get 322.15 meters per second. B is positive 15 degrees. So 331 meters per second plus 0.59 meters per second degrees Celsius times 15. V should be equal to 339.85 meters per second. Okay. C is 25. So V equals 331 meters per second plus 0.59 meters per second degrees Celsius times 25 degrees Celsius. You end up getting a V of 345.75. Okay, so obviously, as the temperature is going up, so is the speed. And the last one, 33. So 331 meters per second plus 0.59 meters per second degrees Celsius times 33 degrees Celsius. And when you do this, you should get 350.47. Okay, that's it for number one. Now number two is similar, except this time it wants you to find the temperature. So it gives us V, so we have V equals 331 meters per second plus 0.59 meters per second degrees Celsius, and we need to solve for T. So the first step is going to be to get rid of the 331. So it'll be V minus 331 meters per second will equal 0.59 meters per second degrees Celsius. And now to get the T by itself, you have to divide by the 0.59. So in this question, we'll be doing 331, whoops, no, I lied, lost the V. We'll be doing V minus 331. V minus 331 meters per second divided by 0.59 meters per second degrees Celsius. Okay? So in A, it tells us the speed is 352. So T equals 352 meters per second minus 331 meters per second over 0.59 meters per second degrees Celsius. And when you do this, you get a temperature of 35.59 degrees, which should make sense because in part D and number one we had 350 and this one's 352. D was 33 degrees, so this one should be slightly higher, and it is. And yes, I'm cheating. I'm using my rearranged because it would be exactly the same steps to rearrange all four of these times. So B is 338. So 338 meters per second minus 331 meters per second, that should be about 7, divided by 0.59 meters per second degrees Celsius. And when you do this, you should get 11.864 degrees Celsius. C, T is equal to 334 meters per second minus 331 meters per second over 0.59 meters per second degrees Celsius. And when you do this, you should get 5.085 degrees Celsius. And D, the last one, T is equal to, this time the temperature is 319, or excuse me, the speed, minus 331 meters per second. We're going to get a negative here because that's negative 12 on the top, divided by 0.59 meters per second degrees Celsius, and you end up with negative 20.34 degrees Celsius. That was going to be a negative, but then it looked like it was attached to the 20, so I made a new negative. Number 3 says, a ship's horn blasts through the fog. The sound of the echo from an iceberg is heard on the ship 3.8 seconds later. Okay, so here's my ship in the water, and here's my iceberg. Okay, so the sound from the ship goes over and comes back in 3.8 seconds. So this is delta T total. How far away is the iceberg if the temperature of the air is 12 degrees? So first we can find the speed. V is equal to 331 meters per second plus 0.59 meters per second degrees Celsius, and it says the temperature of the air is negative 12 degrees Celsius. So when you do this, you get a speed of 323.92 meters per second. So we have the speed, we have the time it takes to go over and come back, so we can do V equals delta D over delta T. So delta T, oops, no, I want delta D. So delta D is equal to V delta T. Now, if you use the whole time, you're going to get the distance over and back, and you'll have to divide it by 2. Or you could divide the time by 2 to start with. Either one will work. So 323.92 meters per second times 3.8 seconds, and you can either put just this over 2 or the whole thing over 2. If you do the whole thing over 2, then on the top you get 1230.896 meters, and that's going to be over 2. And in the end, then your delta D should be 615.448 meters. Okay. Part B says, how might weather conditions affect the accuracy of this answer? Well, it could affect it in 2 ways. It says foggy, and so there might be moisture in the air, which would increase the density of the air, which would make the sound perhaps travel a little bit faster. The other thing is, it said it was minus 12 degrees. Minus 12 degrees on the boat, but perhaps as you approach the iceberg, since it's made of ice, it might actually be colder. So we're assuming uniform speed because we're assuming uniform temperature the whole way along, but that might not be true. All right, number 4. An electronic fish finder uses sound pulses to locate schools of fish by echolation. Right, so here's your boat again, and the little fishy dudes are down here. So it sends a sound pulse down, and the pulse comes back. What would be the time delay between the emission of a sound pulse and the reception? So they're actually looking for the total time here. The time it takes to go down and come back. If a school of fish is located at a depth of 25 meters, so delta D one way is 25 meters. And it says that assume the temperature of the water is 20 degrees. So delta T, or T is 20 degrees. But now be careful. You can't use 331 here. The fish don't live in air. The fish live in water. So you need to go back to your chart 2 pages back on 387. And it says it's a lake.